So this lesson is based on the concepts of limiting reactants and percent yield. It can be found in section 9.3 of the interactive reader on page 297. So first, let's begin by considering the reaction between hydrogen and oxygen to make or to synthesize water. And of course, as we've talked about, it's important to start off with a balanced chemical equation in order to satisfy the law of conservation of mass. So therefore, we have the two coefficients that we've inserted. So one thing that's important to realize is that in the lab, a reaction is rarely carried out with exactly the required amount of each of the reactants. Usually, one or more of the reactants is present in excess, meaning that there's more than the exact amount required to react. So let's kind of take a moment to consider those situations. So let's begin by considering the first scenario in which we have exactly the amount of hydrogen needed to react with each oxygen molecule to produce the proper amount of water. So here we can see is if we assume that the hydrogens are white and the oxygens are red, then what we can see is that because we have a total of 8 hydrogen molecules and 4 oxygen molecules, there are 2 hydrogen molecules that can react with each oxygen molecule to form 2 molecules of water. So for example, these 2 molecules of hydrogen and this 1 molecule of oxygen can react to form 2 molecules of water. And in this case, because we have the exact ratio of 2 hydrogens per every 1 oxygen, then when we look at our products, we see that all of our reactants have been converted to water, and there's nothing left over. Then now let's consider the second example in which we don't have an exact ratio of reactants. So here what we can see is that if we assume again that the hydrogens are kind of the gray-white and the oxygens are red, that we have 10 molecules of hydrogen and 7 molecules of oxygen. You'll notice this is not an exact 2-to-1 ratio. So what we find is that as we begin to combine hydrogens with oxygen to produce 2 molecules of water, we can continue to do that. So I'll try to circle out kind of what we're using. 2 of hydrogen per every 1 oxygen. There's another one. There's another one. But if you notice, once we use up all that hydrogen, then we still have 2 oxygen molecules remaining that weren't able to be converted into the product water simply because there are no more hydrogens left. They've already reacted. And you can kind of notice on the product side that now we have 10 molecules of water, but there are still those same 2 molecules of oxygen remaining. So what we find is that the substance that is not used up completely in a reaction, or the substance that we have left over, is going to be known as the excess reactant. And that will be an important term to know. Okay, so in this case we would say that the excess reactant is oxygen, because it's what was left over or not used up completely in the reaction. So if oxygen is the excess reactant, then we may ask, well, what about hydrogen? So if we think about the role that hydrogen played in this reaction, it limited the amount of product that we could produce. Because if we had plenty of hydrogen and just our 7 molecules of oxygen, we could have made at least a few more water molecules. But because we ran out of hydrogen, that stopped the reaction short and limited how much we could produce. So that's what we're going to see, is that the name of the other reactant will be the limiting reactant. And in this case, that will be hydrogen. And so again, just to emphasize, the limiting reactant is the reactant that limits the amount of product that can be produced. And it also limits the amount of the other reactant that can be used in forming the product. So now let's go on to talk about how this concept of limiting reactant can be paired with what we know about reaction stoichiometry. Okay, so we're first going to work the example on page 298 about silicon dioxide reacting with hydrogen fluoride according to the following balanced equation. So within the wording of the problem, what we're given is that we're going to start the reaction with 6 moles of hydrofluoric acid and 4.5 moles of silicon dioxide. And what we're asked to find is, what the limiting reactant is. Now if we think back to our definition of limiting reactant, it's the reactant that limits the amount of product we can produce. So if we think about how we're going to go about finding the limiting reactant, what we're going to do is to take the amount of each reactant and using stoichiometry, figure out how much product could be made from that reactant. Then we'll compare the amounts of product that could be made and the reactant that led to, or the reactant that produced, the smallest amount of product will be the one that limits the reaction and will therefore be the limiting reactant. So let's give that a try. So we know we have our amounts of 2 reactants. So now let's pick a product so that we can see how the amounts of product that each reactant makes compares. So let's just choose silicon tetrafluoride. So what we're going to do is see if we start with the amount of each reactant, how much silicon tetrafluoride will produce. So let's do HF first. We'll start by just writing what we're given, 6 moles of HF. And then, again, anytime we're comparing different compounds, we're going to have to use the mole ratio from the balanced chemical equation. In this case, we see that for every 4 moles of HF, we should produce 1 mole of SiF4. Okay? So then, if we were to do that math, we would get 1.5 moles of SiF4 that we would produce if we used up all of the hydrofluoric acid. So now let's repeat the same thing, except this time doing it with the silicon dioxide. So again, we'll start with the amount that we were given, 4.5 moles of silicon dioxide. And now we're going to find out the amount of product it would make by using the mole ratio. So for every 1 mole of silicon dioxide, we should produce 1 mole of SiF4. So when we do the math, we should get that we would make 4.5 moles of SiF4 would be produced if we used up all of our silicon dioxide. So now what we have to do is compare the amounts of products that each reactant made. So we see that when starting with silicon dioxide, if we used all of it, it would result in 4.5 moles of silicon tetrafluoride. However, if we started with our hydrofluoric acid and used all of it, we would only produce 1.5 moles of silicon tetrafluoride. So because the hydrofluoric acid results in a smaller amount of product, it will be our limiting reactant. So in this case, HF is the limiting reactant. And so then in contrast, what that means about silicon dioxide is that it's the excess reactant. It's what will be left over. So now let's suppose that we were then asked a second question that said, well, okay, if hydrofluoric acid is a limiting reactant, then after all of it's used up, how much of the excess reactant will be left over? So now what we're going to have to do is compare the amounts of hydrofluoric acid with the amount that will be reacted out of the silicon dioxide. So, we know again that we were starting with 6 moles of hydrofluoric acid. And what we're assuming is that because it's the limiting reactant, all of that 6 moles will be used up, and when it is, then the reaction will stop. So what I want to know is that if I start out with this much hydrofluoric acid, how much of the silicon dioxide will be reacted with it? So since we're comparing those two compounds, we need to use the mole ratio between hydrofluoric acid and silicon dioxide, which in this case happens to be 4:1. Then, when we do the math, what we get is that 1.5 moles of silicon dioxide were used in the reaction when they were reacting with the hydrofluoric acid. But our question didn't ask us how much was used. Instead, it asked us how much was left over. So now what we're going to have to do is to take the amount of silicon dioxide that we started with and subtract the amount used in the reaction to determine how much was left over. So in words, again, that's the starting amount of the reactant minus the amount used up in the reaction will equal the amount left over. And in this particular problem, we started with 4.5 moles of silicon dioxide, but in the reaction with our limiting reactant, 1.5 moles were used up. So that left us with a total of 3 moles of silicon dioxide that are remaining. And within these problems, you may see that some of the values in the original question may be given in grams. But that's okay, because if we think back to our basic stoichiometry section, we know that we can easily convert grams to moles, or vice versa, moles to grams, using molar mass. So when we're comparing two different compounds within the same equation, we have to use the mole ratio. But in order to do that, if we need to convert from grams to moles, or if the final answer is asked for in grams, then there will also be a part where we'll need to use the molar mass to convert between moles and grams. So now, if you're practicing on your own, pause the video and try practice problem A on page 299. Then, to see an example of what we just talked about, where you also have to use molar mass within the limiting reactant problem to convert between grams and moles, check out the practice problem on page 300 and 301 of the interactive reader that will guide you through those steps. So again, that's practice A on page 299, and then the sample problem on pages 300 to 301. Then check back for the next video on how to calculate percent yield.